The highest recorded wind speed in the strongest cyclone to date was 345 kilometers per hour. You can imagine how destructive such wind would be to the area it passed through. Now imagine, instead of 345 kilometers per hour, if the wind speed were 1,650 kilometers per hour. What kind of devastation would that bring? In reality, we are all moving at speeds much faster than that. The Earth orbits the Sun at an average speed of 107,225 kilometers per hour. The entire solar system, including Earth, revolves around the center of the Milky Way galaxy at a speed of 828,000 kilometers per hour. Furthermore, the Milky Way galaxy it is moving at approximately 2.2 million kilometers per hour. Even excluding all of these, the Earth rotates on its axis at an incredible speed. For example, I live in Dhaka, which is moving at approximately 1,530 kilometers per hour due to Earth's rotation. When it comes to Earth's axial rotation, the speed is fastest at the equator and nearly zero at the poles. Using this formula, you can calculate the rotational speed of your location. Simply substitute your latitude in place of alpha. Now, the question arises, why don't we feel the Earth's incredibly high speed? Another question is, if the Earth is spinning at such a high speed, shouldn't an airplane just need to ascend to move to another location on Earth? Yet, in reality, this doesn't happen. In today's video, we'll discuss various phenomena related to Earth's rotation. I'm here with you, and you're watching Shifa'at Sci. Let's consider an example. Suppose you're standing in Bangladesh and throw a ball straight up into the air. The ball takes exactly 1 hour to fall back to the ground. Meanwhile, Bangladesh is moving at a rotational speed of 1,530 kilometers per hour due to the Earth's rotation. Logically, this means the ball should land 1,530 kilometers west of its original position, somewhere in Madhya Pradesh, India. But in reality, that's not what happens. The ball lands exactly where it was thrown from. So the question is, how does Earth's rotation actually work in this context? To understand this concept, you need to know about inertia. Inertia is the property of an object that makes it resist changes to its state of motion. Static inertia. A stationary object will remain stationary. Dynamic inertia. A moving object will continue moving at a constant speed in a straight line. While the idea of a stationary object remaining stationary is easy to grasp, why a moving object doesn't stay in motion indefinitely isn't something we observe often in real life. For example, if you throw an object on Earth, it eventually comes to rest. This happens due to forces acting against its motion, such as gravity friction. However, if an object were in a situation where no forces opposed its motion, it would keep moving indefinitely. A simple example of inertia. Imagine you're in a vehicle. When the vehicle is stationary, your body is also stationary, but as soon as the vehicle starts moving, you tend to lean backward. This happens because, before the vehicle starts moving, static inertia keeps your body at rest. When the vehicle starts moving, your body resists the change in motion and tries to remain in its original state, making it seem like you're leaning backward relative to the vehicle. Similarly, if a moving vehicle suddenly stops, your body tries to maintain its motion due to dynamic inertia. Result, you lean forward. This is the effect of inertia. In the case of the Earth's rotation, a similar type of inertia comes into play. Result, relative to the vehicle, you remain behind, causing you to lean backward. On the other hand, when a moving vehicle comes to a stop, the opposite happens. As the vehicle stops, your body, due to inertia of motion, moves forward relative to the vehicle, making you lean forward. Now, let's consider the rotation of the Earth. All objects on the Earth's surface are moving at the same speed as the Earth itself. This is why we neither perceive nor feel the Earth's rotation. It's similar to how passengers inside a moving train perceive themselves. Passengers inside a train feel stationary relative to one another, but are actually in motion. They only realize this motion when they look outside the train. Similarly, from within the Earth, we cannot feel its rotation. However, if we look at the sky for an extended period, we can observe the movement of stars or the moon, which provides evidence of Earth's rotation. Moreover, from outer space, the Earth's motion becomes directly visible. All humans on Earth are affected by inertia due to the Earth's motion. This is why, from within the Earth, we cannot sense its rotation. Since inertia is the same for both you and the object relative to the Earth, we do not feel the Earth's motion. When you throw a ball straight up from the Earth's surface, the ball retains the inertia of Earth's rotation. As a result, from an external viewpoint, the ball's trajectory appears to follow a curved path. However, from your perspective on Earth, the ball moves in a straight line. This is because, relative to you on Earth, the ball is moving with the same velocity as the Earth's surface. This means that to perceive the Earth's motion, there would need to be a stationary reference object around us, which we don't have. That's why we don't feel the Earth's movement. However, if you look at the sky for a long time, the motion of stars or the moon provides some evidence of the Earth's rotation. There is one scenario where you could directly feel the Earth's motion, if the Earth's rotation were to suddenly stop. In such a case, due to inertia, you would be flung off the Earth's surface depending on your position. Unfortunately, or fortunately, there is no possibility of the Earth's rotation stopping anytime soon. And even if it did, there would be no one left to confirm the reality of the Earth's rotation, nor anyone to hear about it. Now, let's discuss whether the Earth's rotation affects the movement of airplanes. When a plane flies in the sky, it might seem as if it is disconnected from the Earth. So, you might think that the Earth's rotational inertia does not influence the plane. This could lead you to assume that if the plane simply ascends vertically, it would automatically drift westward due to the Earth's rotation. As a result, traveling westward would take significantly less time and save fuel. However, in reality, this does not happen. The idea that planes are detached from the Earth is fundamentally incorrect. When a plane flies in the sky, it remains within the atmosphere. While the atmosphere might appear separate from the Earth at first glance, it is in reality not detached. If the atmosphere were truly disconnected from the Earth, it wouldn't rotate along with the planet. As a result, people in equatorial regions would experience winds moving at 1,670 kilometers per hour, several times stronger than the most powerful cyclones ever recorded. The truth is that the atmosphere rotates along with the Earth. While there are local variations in wind speed, on a larger scale, the atmosphere is essentially anchored to the Earth. However, this anchoring isn't absolute. It's somewhat loose. For example, the atmosphere over Bangladesh rotates along with the Earth and remains roughly above Bangladesh. This means the atmosphere cannot be considered separate from the Earth. Just like the land or roads on Earth are firmly attached to it, the atmosphere is similarly bound to the planet. Therefore, when it comes to movement on Earth, both the ground and the atmosphere should be treated as one system. When traveling on a road from east to west or west to east, it takes the same amount of time. Similarly, moving through the atmosphere in either direction also takes the same amount of time. However, flying from east to west takes slightly longer. For instance, traveling from the USA to the UK takes about 5 hours, whereas returning from the UK to the USA takes longer. The reason behind this is the jet stream. The sun's rays fall directly on the equatorial region and the areas around it, causing the central part of the Earth to heat up more than the polar regions. This temperature difference creates differences in air pressure. As a result of this pressure difference, air begins to flow. Air from high-pressure regions moves toward low-pressure regions. However, as it moves, the Earth's rotational inertia causes the airflow path to bend, a phenomenon known as the Coriolis force. At the boundary between high-pressure and low-pressure zones, this bending creates a type of jet-like flow, which is called the jet stream. These jet streams have significantly higher wind speeds and generally flow from west to east. This concept of the jet stream can be easily understood through a scene from Finding Nemo. In the ocean, there is a distinct current within the water where the flow is comparatively faster, helping fish travel long distances effortlessly. Similarly, jet streams help planes travel quickly from west to east with less fuel. And that is why commercial planes utilize jet streams when traveling in that direction to reach their destinations faster. Another important point to mention is about measuring distances. On a flat surface, the shortest distance between 2 points is a straight line connecting them. However, on a spherical surface, the concept differs. For instance, the shortest distance between the US and India on a flat map would be a straight line. But in reality, the shortest distance on a spherical surface is the path along a great circle. A great circle is a circle drawn on a sphere, such as Earth, that divides it into two equal halves. The shortest path between any 2 points on a sphere is the arc of the great circle that connects them. So, while something might seem correct at first glance, it may not always be so. Similarly, even though we cannot feel Earth's motion while being on it, the Earth is actually engaged in multiple motions. If we sum up all the motions of Earth that we know of so far, it would amount to approximately 850 kilometers per second. These include Earth's rotation on its axis, its revolution around the Sun, the Milky Way's rotation around its center, and the motion of the Milky Way itself. There may also be other motions of the Earth that are currently beyond our knowledge, which could add another dimension of motion to the Earth. Today's world is unimaginable without electricity, but it wasn't discovered in a single day or by a single individual. It is the result of the collective efforts of many people. To learn in detail about how electricity was discovered, give this video 1,000 likes.